So as you can see that whenever you're trying to create a regression, it's always called regressor, right? The model is called regressor, and then whenever you're trying to classify something or create a classification model, the model is going to be called a classifier, right? So lastly, scalar.neighbors. So this is another type of big, I guess, category of models, right? So you can actually import k-means classifier, or k-means has, if you can just k-neighbors classifier. The other one is called k-neighbors regressor, right? For any model in a scalar, typically you have a classifier as well as a regressor, right? That's kind of like, except for a linear model, the name is not so descriptive, because I mean this is very simple. The linear regression, you will know that it's a regression. But logistic regression, even though the name is regression, but it's a classification model, right? Remember that. So then let's use our data from before, right? So remember, like, our data is like, this is our data, right? We have bedrooms, bathrooms, and then rooms, square footage, lot size, year built, and prior sale amount, right? So we want to use these features, right, to predict something. Say we can now define our y. In our prior section, 2.1, we said that we didn't want to consider y because it's unsupervised learning. That means there is no y. There's no non-outcome, right? However, in classification or regression, there is non-outcome. So therefore, we want to consider x and y. And note that x is always like uppercase, right? So that means whenever it's uppercase, that's going to be a matrix. You know that's going to be a matrix. Whenever it's lowercase, it's going to be a vector array, meaning that it's only going to be one column, right? So you can actually do the same thing. So estimated value. So now we have x and y. So let's, just fit something quickly, right? The usual way is, because y, remember, is the estimate value, which is a numerical value, right? Y is a numerical value. So let's just, print out our y. You can see that's a numerical value, right? And then let's just ensure df.info to ensure that the type is actually saved in, right? It's an integer, right? So therefore, it's a numerical value. Okay, that's great. So now we can just say, we can actually initialize this model, right? In every model in a scalar, you have to do this initialization statement, right? And then you can actually do fit, right? So fitting, you'll need to pass two things, right? In regression, because you need the feature. This is our feature matrix, right? We have 7 features, and then y is our non-outcome, right? That's why it's called supervised learning, because you have the non-outcome, right? So you use 2 pieces of information to create this linear regression model, right? By using this function called .fit. Right, so lg.fit, and then you can do lg.score. And then just put that. Okay, now the score is, 80, almost like 80%, right? 76%. It's not that bad, right? But I'm thinking that it's going to be overfit. That means, so there's a concept in data science, overfitting, underfitting. So overfitting means that it's just going it's going after the noise. Meaning, if the model sees a new data set, it wouldn't perform as well, because this model is very, very specific to this data set that we use to train, right? So this part is the training, right? So therefore, we should do a train test split, right? So in a scalar, luckily, there is a package that you can just use, right? It's called cross-validation. I think it's from cross-validation, right? It's from the cross-validation section of a scalar, and then you can do train test split, right? Okay, awesome. So we can run this. And then, so before doing this, we should actually train test, split our x, y. If you don't put anything, the default is going to be 80%. Will go into training data set.